The last speaker of this session is Zhensheng Yuan from University of Science and Technology of China. And his presentation is the staggered immersion cooling in optical lattice and mass production of entangled atom pairs. So please show the presentation. Yeah.
Hello, everyone. This is Zhensheng Yuan from the University of Science and Technology of China. I would first thank the organizers for inviting me to present our work on manipulating ultracold atoms. The title of my talk is Staggered Immersion Cooling in Optical Lattice and Mass Production of Entangled Atom Pairs. This is the outline of my talk. First is the motivation of using entangled qubits for quantum computation and simulation tasks. Let's consider the complexity of a quantum system. For example, we do a numerical simulation of a system with n qubits by a classical computer. Straightforwardly, we may do exact diagonalization of the Hamiltonian with dimensionality of 2 to the power of n times 2 to the n. If n is 150, the size of the matrix will be 10 to the 90. This is the number of all the protons of the universe. This task is out of reach with the state-of-the-art technology by the order of 68. Then our task for quantum simulation is to create a similar Hamiltonian with the atomic system. Afterwards, we do manipulation and calibration of the quantum state. We study the dynamics, correlation, entanglement, phase transition in a precise and programmable way. Furthermore, when we have a large entangled state, we can do one-way quantum computing by single qubit operations and measurements. We know this is equivalent to the quantum circuit model. Therefore, it's important to create large entangled state for quantum information processing. I will show you how we do this in optical lattice. With the technique of optical lattice, we can prepare a large number of atoms in a single run. Each side of the lattice is occupied by a single atom. With quantum gas microscope, we can do imaging and manipulation at single atom level. By tuning the interaction between atoms in neighboring sites, we can create entangled atom pairs. After we have entangled pairs, we then connect them along this chain and afterwards along the vertical direction. Finally, we have a large entangled state in a two-dimensional optical lattice. An incident laser beam and its retroreflected one together form a standing wave of light. The standing waves along three directions form a cubic lattice, and the lattice constant is half the wavelength of the light. This Hamiltonian describes the interactions in the lattice, with the first term is the tunneling between neighboring sites, and the second term describes the on-site interaction when we have more than one atom in the same site, and the last term is the chemical potential. We apply a superlattice to divide the atoms into double wells and flip the spin of every second atom. Then we prepare the initial state of spin up and down in each double well. At these spin configurations, are not the eigen state of the system, the atoms will oscillate in between these two spin configurations. And if we stop at half of the way, we will create the spin entangled state. This is our experimental setup for preparing ultra-cold rubidium atoms. Here is a magneto-optic trap for laser cooling. The atoms are transferred to the sense chamber by magnetic coils, and there we prepare both Einstein condensate by evaporative cooling, and these ultra-cold atoms will be loaded into optical lattice. A pure condensate consists of 10 to the 5 atoms. The atoms are then squeezed and evaporated more into a pancake trap. Along the x and y direction, we apply the lattice beam and we observe phase transition from superfluid state to a mode insulator. The superlattice is formed by overlapping two laser beams with wavelengths of 767 nanometers and 5034 nanometers respectively. And the spin states are defined by two hyperfine split states of the rubidium atoms. In order to operate every second side in the lattice, we develop a new technique called spin-dependent superlattice. Different from normal superlattice, we rotate the polarization plane of the retroreflected beam of the short lattice. Therefore, the two species of the spins experience different trap depths in the double well, as shown in the figure. The spin-dependent superlattice has a local magnetic gradient in every double well. Therefore, we can apply a microwave pulse with a proper frequency to selectively flip the right or the left atom on demand. And along the x direction, we create as the initial state. After we prepare the initial state, we can lower down the potential barrier in the middle to let the system evolve under the driving of the super exchange interaction. We then stop the evolution by ramping up the barrier again at a proper time for achieving a desired entangled state. When we have the entangled state, we measure spin correlation curve, and finally, we observe the violation of our Bell's inequality. Furthermore, based on the spin-dependent superlattice along two directions, we achieved an array of plaquettes, and within each plaquette, we applied the local magnetic gradient to suppress single tunneling and super exchange interactions. For the first time, we realized a system which is governed by the first order perturbation to the Bose-Haber model, and this is the minimum Hamiltonian of the toric code model, which will be very useful for fault-tolerant quantum computation and for creating topological matters. Until now, one may ask, why not directly connecting the atom pairs to create large entangled states? Actually, there is a challenge that the temperature of the lattice is still high. We still have some defects in the lattice. Therefore, we should cool the atoms more. On the other hand, for simulating high TC superconductors with doped Fermi-Hubbard model, we need to cool the atoms more to reach the regime for observing D-wave superconductors. Therefore, the two applications have the same request of cooling atoms more in the lattice. Then I will show you our newly developed technique of staggered immersion cooling in the lattice. There have been some theoretical proposals to remove the entropy from the center of the sample to a surrounding reservoir. A similar idea is proposed to reshape the lattice profile for keeping low entropy in the center. One can also immerse an insulator into a fluid. The gapped insulator will be protected from being excited. However, the proposals are really hard to achieve in experiment, or the efficiency of entropy exchange is really low. The basic principle of the scheme is based on two coupled subsystems. One is a gapped mode insulator, and the other one is a gapless superfluid. Most of the excitations are in the reservoir of the superfluid. In order to improve the entropy exchange between the sample and the reservoir, we have a naive picture. Let's say a sample is immersed in a coolant. The heat exchange is around the boundary. So if we slice the same sample into small parts, the exchange boundary is much larger than the earlier one. So the efficiency of heat exchange will be much better. This is our experimental realization of the cooling scheme. During the phase transition from superfluidity to mud insulator, while we're ramping up the trapping potentials, we keep a tilt in each double well. So the atoms are grouped into two subsystems. The left rows are the samples, and the right rows are the reservoirs. The samples enter into the regime of mud insulator earlier than the reservoirs. However, the exchange of particles among the two subsystems transfer entropy from the samples into the reservoirs. Experiment. We start from the superfluid state. We ramp up the lattice potentials, then the entropy will be redistributed among the samples in the reservoirs. Afterwards, we remove the reservoirs with higher entropy and leave the samples with very low entropy. We then redistribute the atoms into the whole lattice to achieve a system with unit filling. Here shows the cooling effect. The left panels shows that during the phase transition, we use the balanced superlattice. Therefore, the entropy distribution is homogeneous along the whole lattice. Comparatively, based on the cooling scheme, we use a tilt superlattice. The samples have a much lower entropy, while the reservoirs have much higher entropy. The measured atomic densities confirm our expectation. If we use Monte Carlo simulation to simulate our experimental process for an initial gas, after the cooling, we have the reservoirs with a higher entropy, while the samples have a much lower entropy. For different tilt of the superlattice, we studied the atom redistribution in the samples and reservoirs by Monte Carlo simulation. The curves here have a few steps which indicates the gap protection from excitations. The experimental result confirms as well the steps, and the sharpness of the edges are used to calibrate the temperature and entropy. This curve shows the entropy per particle before and after the cooling. We can see that when the initial entropy is higher than 0.2, the cooling effect is limited, and the reduction of the entropy is by 1 to 3 times. However, when the initial entropy is lower than 0.2, the reduction of the entropy is dramatically. We finally found a 60-fold reduction of the entropy due to the cooling. This cartoon illustration showed that after the cooling, we have the mud insulator with low entropy, while the superfluidity with higher entropy. We then flip the spin of the atoms in the superfluid. User on resonance laser beam to blow. Therefore, we leave only the mud insulator with very low entropy, and we use a adiabatic passage process to transfer the 2-0 configuration to 1-1 configuration, and finally we achieve a unit filling lattice. In the experiment, we did this adiabatic passage from 2.0 to 1-1 back and forth by 50 times, and then we derive the fidelity of this process is 99.2%. Finally, we have a lattice system with unit filling, and based on that, we flip the spin of every second atom. This is the initial state. For the next step, applying a fast entangling gate. Therefore, we have atomic spins. In order to calibrate the fidelity of the entangling gate, we made a gate operation by 29 times, and finally we derived the fidelity is 99.3, and we achieve 1,250 pairs. Finally, I would like to conclude my talk and present the outlook. What we did in the experiment is for quantum computation and simulation with large entangled state. We achieve in the lattice staggered immersion cooling to remove most of the defects. We created atomic entangled pairs, and also we studied random exchange, and we created a minimal toric code Hamiltonian. We have a new step of connecting the atoms with very few defects to a long chain. And in a 71-site quantum simulator, we studied lattice gauge theory. In the near future, we will continue to study strongly correlated topological matters. For example, based on our experiment of random exchange interactions and the toric code, we may couple different plaquettes by the Foucault mechanism and to build a large system of topological matters. At the same time, we may try to extend our experimental techniques to philharmonic system, and there with honeycomb structure or triangle structure, when we study nanobillion anyons. Another interesting update is that we have integrated a high-resolution imaging system into our spin-dependent superlattice. Therefore, when we have a chance to create a large entangled state, for example, 10 by 10 particles, however, there will be a challenge is how to identify the state. We can also use such a system to study spin dynamics. It would be fantastic if that our staggered immersion technique can be adapted for cooling fermions. Finally, I would like to thank my colleagues, Jian Wei and I, as the co-supervisors of this research project. Bing Yang was a postdoc at University of Heidelberg. He moved to Innsbruck beginning of this year. Sun Hui, Han Yi, and Han Ning all contributed to the experiment. Chunjung Huang, who was a PhD supervised by Professor Eugene Deng, they did the Monte Carlo simulation. Thank you very much for your attention. I'd like to take your questions.
Yeah, okay. One question. Thank you. Thank you, Jensen. Yeah. So, I have a question here. And in your system, you have very efficiently removed entropy from each lattice site and make a unit filling of the mod insulator. That's really amazing. And is it possible to implement this technique also on the fermionic system?
Yeah. Thank you. So let's say for a few of the species of harmonic system, it might be a little hard as the spin dependency is hard to be generated in some a few species of harmonic systems. But however, it might be possible for using mixture of bosonic or harmonic system. We cool the bosonic system, and at the same time, we do the sympathetic cooling with a combination of our technique and the sympathetic cooling. That might be possible. We'll think about that.
Yeah, okay, thank you.